All right, let's jump right in. We're going to talk about something you probably use every single day, table salt. But the story of how it gets to your kitchen table, it's like this incredible chemical drama with two wildly different characters coming together in the most spectacular way.
So, this is the big question, right? The central mystery we're going to unpack. How in the world can two super dangerous things, one that's a volatile metal and the other a poisonous gas, somehow combine to make something we sprinkle on our fries? It sounds completely bonkers, but it happens every day.
Okay, so meet our first character, sodium. And we're not talking about just any old metal. This stuff is so reactive, it literally explodes if it touches water. Then on the other side, you've got chlorine. That's a straight-up poisonous gas. Yeah, the kind used in chemical warfare. So those are our starting ingredients. Not exactly something you'd want in your pantry, right?
But when these two get together, something amazing happens. They create this, sodium chloride. Yep, just good old table salt. So what's the deal? What's the chemical magic that turns these two total hazards into a kitchen staple? Let's get into it.
All right, to really understand this, we've got to zoom in. I mean, way in. We're talking about going down to the atomic level to see this shocking transformation for ourselves. It's time to meet the key players.
Okay, first up, we have what's called a cation. That's our metal, the sodium. Think of it this way. It loses an electron. And since electrons are negative, losing one makes the whole atom positive. Just remember, metals are kind of like generous givers. They're always looking to offload an electron to get stable.
And every hero needs a partner, right? Well, in this drama, that's the anion. This is our nonmetal chlorine. It does the exact opposite. It gains that electron that sodium just ditched. And by grabbing that extra negative charge, the whole atom becomes negative. So let's keep it simple. Cations are positive, anions are negative. Got it? Awesome. So, we've met our players. Now, let's get to the action. I love this part. I call it the Great Electron Heist. And trust me, it's the perfect name for what's about to go down. Here's how the heist plays out. Sodium has this one single electron in its outer shell that it's, not really holding on to very tightly. It's just kind of hanging out there. Meanwhile, chlorine is over here, and it desperately wants just one more electron to feel complete. So what do you think happens? Whoosh! That lonely electron literally jumps ship. It leaps from the sodium atom right over to the chlorine atom. And bam, just like that, sodium is now a positive ion, we call it Na+, and chlorine is a negative ion, Cl-. Heist complete.
Okay, so now we've got a positive ion and a negative ion. And this is where the magic really kicks in. You know that feeling when you bring two opposite ends of a magnet together? That snap? That's basically what's happening here. This incredibly powerful attraction between the new positive and negative ions, well, that's what we call an ionic bond. And that really gets to the heart of it. It's not like they're holding hands or anything. There's no physical link. It's just this super strong force, an attraction that locks them together. And that attraction is what creates the compound. It's what turns two dangerous, unstable elements into something totally new and totally stable. So let's zoom back out for a second. Because this whole electron heist thing isn't just happening between two little atoms in a vacuum. No, this happens on a massive, epic scale, building this incredibly organized empire. I mean, just picture a single, tiny grain of salt. Looks simple, right? But if you could look inside, you'd see billions, literally billions of these sodium and chloride ions, all formed by that exact same electron transfer we just talked about. It's mind-boggling. And here's the cool part. They don't just form a messy pile. Nope. They build this super organized, rigid 3D structure that we call a crystal lattice. Imagine a checkerboard, but in 3D. Every positive sodium ion is perfectly surrounded by negative chloride ions, and every negative chloride ion is perfectly surrounded by positive sodium ions. On and on it goes. This perfect pattern is why salt crystals have that classic cube shape. And since it's always one electron jumping from one sodium to one chlorine, the ratio is always 1:1. That's why we write the formula as just NaCl. But hey, it's not always a simple 1-to-1 swap. Chemistry likes to keep things interesting. Take aluminum, for example. It's a bit of an overachiever. It wants to get rid of 3 electrons. But our friend chlorine can only catch 1 at a time. So what's an aluminum atom to do? It needs to find 3 different chlorine atoms to take its 3 electrons. So 1 aluminum bonds with 3 chlorines. And that gives us aluminum chloride, or AlCl3, a compound that, fun fact, is probably in your antiperspirant.
Okay, so we've seen the atomic heist and the crystal empire. Now, let's bring it all back home. How does all this tiny, atomic-level stuff affect the world we can actually see and touch?
So think about this. What happens when you stir salt into water? The water molecules, which are kind of like tiny magnets themselves, swarm the salt crystal. They just surround it and they start pulling. They literally rip the positive sodium ions and the negative chloride ions away from each other, completely dismantling that perfect crystal structure. Now all those ions are set free, just floating around in the water.
And this is where things get really interesting. You might think water conducts electricity really well, but pure distilled water is actually a terrible conductor. But the second you add salt, bam, it becomes a fantastic conductor. What's up with that? Why the huge change?
Well, it's because that salt has become what we call an electrolyte. See, electricity is just the flow of charge. And what did we just set free in the water? A whole bunch of charged particles, those positive and negative ions. They're like little Ubers for electricity, carrying the charge from one place to another. Without those free-moving ions, the electricity has nowhere to go. It's the ions that do all the heavy lifting. And listen, this isn't just a neat science trick. This is seriously important safety information. Think about lake water or the water in a swimming pool. It's packed with dissolved minerals and salts, tons of electrolytes. That's what makes it so conductive. And that is exactly why you have to get out of the water immediately during a lightning storm. It's incredibly dangerous.
So let's do a quick recap. Everything comes back to that super strong ionic bond. It's why ionic compounds are usually hard, brittle solids. It's why they have crazy high melting points. And it's why, when you dissolve them in water, they create these electrically conductive solutions called electrolytes. So next time you grab the salt shaker, just take a second to think about it. You're not just adding flavor. You're sprinkling on a crystal empire, built by a great electron heist that happened between billions and billions of ions. Kind of makes you wonder, doesn't it? What other amazing chemistry is hiding all around us, just in plain sight?